All right, we'll talk a little bit about compensation tables in Power PMAC. So Power PMAC has table-based corrections for machine or sensor imperfections. For example, lead screw compensation. Power PMAC can have up to 256 total compensation tables loaded at any time. Power PMAC has the ability to do linear, one-dimensional, two-dimensional, and three-dimensional tables. So linear, planar, and volumetric compensation tables. And each table can be selected to roll over or not in each of its individual dimensions. First or third order, these tables have first or third order interpolation between points. So first order correction value is always continuous. In third order, the rate of change of correction is also continuous. Corrections are computed every servo cycle, not just at move endpoints. And the correction values are floating point scalable units, as opposed to in Turbo PMAC it was integer values based on encoder counts or fractions of encoder counts. Now it's a floating point value. You can scale it to anything that you want, typically your machine units. And the tables do not have to start at the zero position of the source motor. Direct software array access to the table points. So now you can manage the table points dynamically if you wanted to, if you so desired. You could have software running, for example, in a PLC or even a C program that dynamically changes your table contents, let's say based on temperature. And you can now select how many tables that you want to enable, as opposed to Turbo PMAC where you would basically enable all the tables or not enable any tables, enable and disable all the tables at once. And so there's a sys.comp enable structure element. That is the number of enabled tables. So it always enables tables starting at 0 to that number minus 1. So if you set it equal to 5, tables 0 through 4 will be enabled. And typically you'll probably use table 0. Well, I shouldn't say typically, but you can not have a table. If there's nothing in a table 0, there's very little overhead in Power PMAC for enabling tables 0 through 4. So let's say you wanted to have 4 tables enabled, 1, 2, 3, and 4. Setting it equal to 5 would enable tables 0 through 4. Corrections are functions of motor desired position. So this is so that it doesn't interact with servo loop dynamics. And there's flexible specification of where the correction is applied, where the target of the correction goes. So actual position offset for position of velocity loops, and these do not affect feed forward. Servo torque command offset to compensate for cogging of a motor, for example. You can have backlash compensation offset. So when I talk about the target registers, these are what the targets that this table is currently writing to. So we have the position loops or the position and velocity loops, the torque output of the PID loop, the backlash compensation, and desired position offset to basically create electronic cam tables. Desired position, very, very much like commanded position. There could be multiple targets for a single table. You can have up to 8 targets for a single table. So it could end up putting its values into 8 different other target registers. Note that there are multiple registers for a single motor. For example, there's both position and velocity loop, or you have multiple motors like a gantry pair, and you need the same compensation on both of the gantry pair. And multiple tables can have the same target register. So you can have several tables that are compensating the same location. So you can have one on top of another. Correction should be additive. And the first table overwrites the previous cycle's correction. Subsequent tables will add. And there's a out control bit in the setup for it that lets us tell it how that, which ones do that. So an example of this, you have coarse and fine corrections for a motor. So one table will be a coarse correction, the other subsequent ones would be a fine correction. So the structures that we have for compensation table, we have the source motor index number for the particular dimension. So for table M is 0 to the number of tables that you have, and then N in this case refers to the source motor index number, and then the number of zones in that dimension, and I'll show you a graphic here in a second that'll make a little bit more sense. The starting minimum position, the starting position of the source in that dimension, and then the span of that source. So this is where the table is considered to start in that dimension. And then data structure elements for the targets. For the comp table, there's target, dot target, and it's the address of what the target register is, and then there's an output scale factor for that target register. So you can multiply the entire output by a floating point. Each table has a control and output control mode byte. And we'll talk about, we'll look at the details of that here in just a couple more seconds. And then the actual data for each table entry. So for a one-dimensional table, data sub I. For a two-dimensional table, it's data sub j sub I. And then for a three-dimensional, k, j, and I. Now I'll go into just a little bit more detail. In the handouts that I gave you, there is a compensation table . And so we talked about that, and I won't go into all of the gory details here, but and this is well described in the Power PMAC user's manual on using compensation tables, but you can calculate the exact memory required for a table by using the equation that we provide. The default memory allocation that the IDE sets you up for in Power PMAC is 1 megabytes worth of table. We talked about specifying the sources. So here's a nice graphic showing basically what's going on with the two-dimensional compensation table. You have motors X and Y, and they are providing the source data. And then in this case, we're compensating the Z-axis for, let's say, issues on the planarity of the table, the plainness of the table. It's not very plain for whatever reasons. We talked about specifying the targets. And so we can see here, the target could be the outer loop position, the comp pos register, or comp pos 2 register, which is the inner loop, the velocity loop. So there's the position loop, velocity loop. For a torque compensation table, we would use the address of comp DAC. So notice how each of these source registers have their own comp name in the structure element name to indicate to us that it is the compensation register for that feature in that particular PID loop or that particular motor number. So we have comp DAC, we have BL for backlash comp, and then we have comp des pos for compensating on the desired position. By the way, if you're not using compensation if a compensation table feature is not turned on, then you can write to these registers in your own code. So here's a look of where these show up in the PMAC PID loop. So we can see here, here's comp desired position. So that's like it's like a commanded position input into the PID loop. Here's comp pause and comp pause 2. So there's the compensating the actual position. There's compensating the velocity part of the loop, the inner loop. There's backlash compensation going in on top of position compensation. And then here we are coming to the direct output of the PID loop, and there's where the comp DAC register is. So typically, a cross-axis compensation would be used, for example, in a bowed lead screw, where as you move along the x-axis, the y position is going to end up being different. So that would be an example of cross-axis compensation. The control byte for compensation tables determines how the corrections are calculated. So we can, bits 1 and 0 determine whether or not it's what the order of interpolation is from the sources. Bits 2 and 3 determines the boundary mode. Bits 4 and 5 for the first source. Bits 4 and 5 boundary mode for the second source. And bits 6 and 7 the boundary mode for the third source. So are we going to roll over at the table boundaries? Are we going to maintain the last correction at the table boundaries? Or are we going to mirror the table at these boundaries, like bouncing back into the table? And if that source is not used, if it's just a one-dimensional table, then it really doesn't matter what these are set to, because they don't exist in the calculation of the table anyways. So the important point to take out of this is comp table sub m dot CTRL determines how we use the compensation table, how we're going to interpolate each source, and what happens at the end of the table for each source. Using multiple tables in the same target. So you can add corrections from multiple tables into a single register. We talked about that in the first section that we just looked at. So it's like having a coarse and a fine correction on that particular dimension. So each table will have the same target address, and then the output control. The lowest numbered table should be set to overwrite the target. Bit Q of the comp table M output control should be set to 0, and the subsequently higher numbered tables must be set to add to the target value. Bit Q is set to 1. So you can effectively enable and disable tables. There's a sys comp enable n, which will enable tables in order of the table numbers from 0 to n minus 1. But there's a little bit more flexibility now in enabling and disabling a table. One of the things you could do to immediately disable any compensation table would be to set the single element name scale factor comp table sub m dot sf sub q to 0. Just set the scale factor to 0, and any calculations going on in the compensation table, the output is just set to 0. So that immediately disables the table. The other thing you could do is you could set the target register address to 0, which effectively tells Power PMAC to disable that table, because now there is no target address. In most address structures in Power PMAC, if you set them to 0, that almost always the firmware takes that to mean that you're disabling that addressable feature in Power PMAC. Now, when you use the scale factor, it forces the correction to 0, but it can ramp down gradually, and it can ramp up gradually when you turn that back on. The second method just leaves the last correction in place because you've stopped outputting to the compensation register. Remember, this just sets the scale factor to 0. This actually points the output away, and whatever was the last value in the compensation register stays there. And you could overwrite that if you wanted to yourself manually. And then last but not least are all the data elements in the table. So data sub-elements are all the table entries. So let me show you an example here. Here's a good example at the bottom, comp table.data. And so it's a three-dimensional table. And we're going to start at this dimension of 4, this dimension of 3, this dimension of 0. And this will incrementally add these values starting at 0, 1, 2, 3, and 4. And so this is the values that this one will be changing as you add values up to the end of the number of zones that we've created for that table. So notice you'll have so many data points in the table. You'll have n minus 1 zones then in that table. Notice here with rollover now, it rolls over back. Data 0 goes back to data 1. Data 0 goes back to data 4 in this direction. Just like every other structure element that takes indices can only be specified with integer constants or local variables, an L variable. So we can see here, comp table M data I can be a value from 0 to 16 million. Any local variable L through L8191. In two-dimensional tables, now we have broken up the indices, so 0 to 65K for the two indices, local variable L0 and local variables L0 and L1. And then 0 to 65K, 0 to 253, and 0 to 252 on the three-dimensional table, and then local variables L0, L0, L1, and L0, L1, and L2. And the value of the index must be within the declared range for that dimension. Remember, we set that up in an earlier structure element name. So basically, the new corrections are computed every servo cycle. So here's an example. I think this gives you an excellent idea of how we put together a compensation table. We can see here we're at compensation table 0, source 0. So motor 1 is the source. This is a one-dimensional table. And then we tell the number of zones, comp table 0.nx is the structure name. And it's 0 because, remember, again, it's a one-dimensional table. And we tell it has 11 data zones. So it's going to have 12 entries. There's no second dimension. There's no third dimension. So we set the nx for 1 and 2 to both to 0 to tell it it's only a one-dimensional table. And then the table starts at minus 10,000 counts. So that's the start of the table. And it has a span of 110,000 counts. That's the x.x0.d little x structure element names. And then we set the target registers, and we want this to compensate both the position and velocity loop. So we want it to be a standard type of screw compensation table. So, and it's going to compensate motor 1. We've told it motor 1. So motor 1 comp pos A, motor sub 1 dot comp pos 2A, both the position and velocity loop. And then we give it a scale factor of 1 for the velocity loop and a scale factor of 1 for the position loop. And then we set the control bit. In this case, this value of the control bit disables rollover and sets it up for cubic interpolation. So we can see 2 bits, or the 3 bits are set on in that. And then the output control is set to 0 to overwrite the target registers each cycle, because this is a one-dimensional table and we just want it to overwrite at each position every time it moves along. And then we give the values to the table. So we start here at index 0, and then we give it sequential points 0 to 5. And then we start at index 6, and we give it the remaining points 6 through 11. So that's 12 total points because we had 11 zones. And then we enable the table by setting syscomp table equal to 1. Remember, that'll enable table 0 only. I like to call these 2 keeper slides because it gives you a really quick overview of how you would set up a compensation table. Now, another nice feature of the IDE, and let's bring up the IDE real quick here. So if I go up here, delta tau, configure, comp tables, and we're telling it's a 2-dimensional table. Notice it brings up this nice 2-dimensional entry dialog that'll let me, once I've told it my source motors and destination motors, and it sets some default values in here. So basically, I think I have 10 zones. Let's see. Yeah, 10 zones in each dimension, and it spans 1,000 counts in each dimension. And then now it will allow me to enter numeric values into the table. And then I could download this table. Let's see. So it gives me a quick and easy way of entering a compensation table. If I do a save, by doing a save now, what I've done is, if you remember every time you type save in the IDE, that takes everything that's been saved in PowerPMAC and puts it in the ppsave CFG file. And so now I can go over here and I can open up the ppsave CFG file that was just modified. I can go down and find my compensation table. There it is. So that's the compensation table I just downloaded. It has 10 zones. Starts at 100 points. And I only entered in 3 values. We can see them there. You can set up what we would call a 0-dimensional compensation table. And so it still has a single entry, data 0, and the value is scaled and written to the target registers. So this could be a useful way of injecting calculated offsets or corrections into either position torque, backlash, or backlash compensation registers. And then you just simply write to the value, the data value of the table. And then every servo cycle, that value is then scaled and written into the PID loop. You could also make it for doing special cascaded servo loops where you stick 2 servo loops together. We have an application note that you can download from the form that describes some of the techniques of using compensation tables for doing this.